Let's talk a little more about structures. So we started discussing the struct statement, and one thing I mentioned you can use structs for is the idea that with arrays we don't have an inherent length to an array, and so we could bundle that into the structure itself. The other thing that we like to do with structures sometime is get away from the idea of parallel arrays. So what are parallel arrays? Suppose that you want to make a program that's tracking scores for students. And so what kind of information do we need? We need to keep student names, and we need to keep student IDs, and we need to keep the scores for the student on some test, for example, or in some course. And we can do this with plain old C, right? We could have integer student ID 100, which would hold 100 student IDs. We could have integer score, which would hold the score for each student. And we could have the names, and the names might be a two-dimensional array of characters, because strings are kind of weird in C. So a two-dimensional array of characters where each element of these 100 rows of our matrix is a 45-character string, right? And this is, a little bit confusing, makes your head hurt a little bit. These are pretty straightforward. But if you get these set up, what can you do? You can have, integer number of students and initialize that to 0. And then when you want to add information for a new student, what do? Well, you store their student ID in this array, you store their score in this array, you store their name in that array, and you increment the number of students, so it would be 1 after you've added one student. And so these are parallel arrays, right? It's 3 sets of data that we keep in sync, right? And if we want to know something about the student whose name is in element 5 of this names array, well, their score would be element 5 in the score array, and their ID would be element 5 in the ID array, right? So this is a common notion. We do this in C, and it works pretty well, but there's a few details to this. One, we have to keep all of these things in sync. So if we decided to alphabetize our database of students, we would sort this names array, but however we rearrange that, we also need to rearrange our score and our student ID array. And so there's potential for getting into trouble, and at the very least, requiring a lot of extra work to keep everything synced up. So that's one potential issue. The second issue is, this is 3 variables that we need to carry around everywhere that we want to do something. So yeah, this is where we're going as structs, right? If I want to print out this information, I have to pass all 3 arrays to my print, and I have to know what order to pass them in, and so on. And this, this is what we did when we were Fortran programmers, right? But we can do something more nuanced. So this is where the structure statement comes in. So we could make a struct student. And what would a student be comprised of? Well, maybe an integer student ID, maybe an integer grade, and maybe a car name. And our name could be 45, or it could be a car star name, and we could dynamically allocate space, but we'll just keep it simple, simpler. And just allocate a fixed amount of space for the student's name. And we'll end the structure statement with a semicolon. All right. And now if we want an array of students, what does it look like? We want variables of type struct student. I'll just call it data, bracket 100. And now this one variable data is an array of 100 entries. And each of those entries is a composite data type called a struct student, which has a student ID, a grade, and an array of characters containing their name. And so if I want to pass this information, this whole set of information for a group of students, to a function, all I have to do is pass it data. And if I want to sort, my information by grade, for example, I just rearrange the elements in this data array, and these three pieces get dragged along with each other as a single unit. So structure is really sort of grouping all of this data into one entity. And like I say, this is a foreshadowing of what we're going to do with objects in 223. Because 223 will have structures where we group data together, but we also group code with that data. And we have what's called an object. So yeah, here we're creating a structure and then creating an array of that structure. And so this works more or less how you might hope that it would work in C, right? The basic way that I think about this is struct student is a type of variable. So we looked at types yesterday. We had ints, we had cars. Well, we have a new type now called a struct student. And anywhere that I would use an int or a car to declare a variable, to declare an array of variables, I can use struct student. If I want to know how big this is, instead of saying size of int or size of car, I can say size of struct student and see how much memory I need. If I'm allocating this array dynamically, we'll talk about that in another week. So it's a composite type of data, okay? And if we have a variable that's a struct student, we can use an ampersand in front to see its address. And we can get a pointer to a struct student. And if we have a pointer to a struct student, we can say star pointer and see what it's pointing to. And we'll be doing that a lot for the rest of the course, so we'll come back to it in a bit. But this is sort of our motivation for having structures. The other thing is, typing int is easy, typing car is easy, typing struct space student is kind of not as easy. So there's another statement we can use, which is a typedef. And typedef will let us define an abbreviation, basically, for a different type of data. I don't use typedef, so I have to actually look up the order of these, but I think it's typedef old new. So we can say typedef struct student and whatever we want to call a struct student. So I could just call it blah, and then instead of saying struct student data bracket 100, I could say blah data bracket 100. So typedef lets us make sort of a shortcut to this notion of a struct student. And usually what you see is something like, typedef if you have a struct student, maybe we would call that type an uppercase student. And then you could say uppercase student. Whatever variable you want to be that structure. But anyway, it's a shortcut. It doesn't do anything that you can't already do. But if you don't like typing struct student, struct student, struct student, you can define a new type that means a struct student. All right, any questions on that? Because we're going to change gears now. All right, so change of gears now. This is going to lead us into our first data structure, which is called a linked list. Let's talk about order of complexity. And we've touched on this in other courses, but let's go through this from the beginning. So when we talk about order of complexity, we're studying how much work has to be done for some algorithm to run. And part of the goal of this is to be able to analyze different types of algorithms. So we'll spend about a week talking about sorting. And we learned bubble sort in earlier programming courses, but there's other types of sorts. There's insertion sort, selection sort, merge sort, heap sort, quick sort, radix sort. There's lots of different approaches to sorting information. Why do we have all these different types of sorts? Well, we learned bubble sort because it's really easy to understand and it's pretty quick to code. But it's fairly inefficient compared to other kinds of sorts. If we had a million pieces of data and we wanted to sort them, using a bubble sort would be really inefficient. Using a quick sort would be really efficient, but a quick sort is much harder to code. Well, it's somewhat harder to code, depending on if you've coded them before. If your data is almost sorted to begin with, there's some sorts that work better than others. There's sorts that will take advantage of that. A quick sort will have terrible performance if your data is almost sorted. It'll work like a bubble sort. Whereas other sorts, like a heap sort, will be very efficient. So one way that we analyze these different types of algorithms is by looking at their order of complexity. And order of complexity is related to speed, but it's not the same thing. Okay? So measuring the speed of an algorithm, how quickly does a bubble sort work compared to a quick sort, is a little less meaningful than you might think. Because how long does a bubble sort take? Well, it depends on what processor you're running on. It depends on how your bubble sort was coded. It depends on how quickly you can manipulate the data. If your data is in memory versus if it's on a hard drive versus if it's in the cloud. So the actual time that we get from a sort is not all that interesting to us in comparison to the order of complexity, which is basically how does the time change as the size of the data changes. So yeah, this is what we call big O notation that we're heading up to. As the size of a data set changes, how does the complexity or the time requirement to process that data change? And let me give you some examples. It may be that if we have twice as much data, it takes twice as much time to process that data. If you have 3 times as much data, 3 times as much time. And that's kind of fair, right? That's sort of what we would expect. If you can do this job in 1 day, you should be able to do this job in 2 days. That's sort of, a human expectation, right? Doesn't always work. Right now, if I'm building, my printed circuit boards at home with a soldering iron and tweezers, and it takes me an hour to build one, I can probably build 8 in 8 hours, right? Assuming I don't stop to eat. But could I build 800 in 800 hours? Probably not, right? Because I have to, teach school and things like that. But this is one way that things might change, and we call this linear time complexity. And we write this with this funny script O with an n in parentheses after it, and we say this is an order n operation. And we'll see why that's called an order n in a minute. Let me show you a different example. Different example might be double the data and you end up taking 4 times as much time. If you triple the data, it takes 9 times as much time. This is what a bubble sort does. If you can bubble sort 100 pieces of data in 1 second, you could do 200 pieces of data in 4 seconds. I was having trouble multiplying 1 by 4. Right? Now a linear sort, right, if it takes 1 second to do 100, it takes 2 seconds to do 200. With a bubble sort, if it takes 1 second to do 100, it takes 4 seconds to do 200. It takes 9 seconds to do 300. If you wanted to do 1,000 pieces of data, that's 10 times as much data. It's going to take you 100 times as long. Right? And so this is what we call quadratic performance, and we write this as an order n squared. And you can see the square happening here. 4 times the data, 16 times as much time. Now, why does a bubble sort act quadratically? Because it's basically a pair of nested loops. So we have a loop where some outer variable goes from 1 to n, and inside there we have some inner variable which goes from 1 to n. And as we go through this inner pass, we compare element I with the next element I plus 1. If they're out of order, we swap them. And we do that, you know, for n pieces of data to make one pass through. And then we have to make a total of n passes. And each pass, the largest number bubbles down to the bottom, or drops down to the bottom. And the smaller numbers bubble up to the top, right? So this is basically n squared passes. N squared times, we're going to do this inner piece, which checks to see if our numbers are out of order and swaps them if they are. So if you have 10 pieces of data, this inner loop runs 10 times, the outer loop runs 10 times, that's 100 executions. If you have 20 pieces of data, this inner loop goes 20 times, and that inner loop runs 20 times itself, so that's 400 times you execute this middle. Okay, classic n squared. And there are details in here. Okay, for example, if your data is sorted to begin with, you're not going to have to do any swaps. Right? Nothing's going to be out of order. So this inner loop will run a little quicker, but it's still 20 times through this inner loop. And it may be that you have a smart algorithm that once you've gone through your inner loop and haven't swapped anything, you exit. And so at that point, right, you don't have to go through all n iterations of your outer loop. But on average, right, you're going to go through probably half of n times on your outer loop. If your data is totally sorted to begin with, you'll go through once. If it's in really horribly sorted case, you might go through n times, and there's an average somewhere in between there. But in the limit, right, as you let n go to infinity, this time that a bubble sort is going to take is going to get closer and closer to n squared. It's going to be n squared plus or minus some factor, but that factor will become less and less significant. All right, so this is order n squared. Some examples of better performance would be order of n log n. This is things like heap sorts and quick sorts. Can I clarify the if statement? So just think bubble sort, right? So your inner pass basically moves through the data and compares each number to the number after it. And if they're in the wrong order, say you're sorting smallest to largest, if this number is bigger than the number after it, you swap them. And then you go on to the next number. If that's bigger than the number after it, you swap them. And you keep doing this till you get to the end of your inner pass, and now your biggest number is at the bottom. And so each pass, one more number moves into place. So there's heap sort, quick sort, things like that are an n log n operation. So if you increase n by a million, right, and your algorithm is n squared, 1,000,000 x, n squared increases you by 1,000,000,000, right? So 10 to the 12th times longer to execute. That's pretty bad. If you're Google, you don't want to be using a bubble sort, right? Because guess what? Google's data sets grow by these huge factors, right? When they started, they had a small amount of information indexed, and how much information does Google have now, right? So if they were using n squared algorithms, there'd be a real performance problem. N log n is a lot nicer. So if you increase by 1,000,000 x, well, what's the log of 1,000,000? It's about 20. N log n is about 20 million. It's not quite linear, but it's pretty close, right? 20 million versus 1 million, well, I can live with that. If it took a microsecond, now it takes, 20 microseconds for n log n as opposed to just being linear, right? That's not a big deal. But something that takes a microsecond, if you increase that by, 10 to the 12th, we're down to the lifespan of the universe almost. So this is a nice order of complexity. This is an even nicer order of complexity. So we'll see this for individual operations on binary trees, where if we have 1,000,000,000 pieces of information, it takes on the order of 40 operations to manipulate that data. And if we go up to, 1,000,000,000,000,000, it takes twice as long. Who cares? Not a big deal. This is our nicest performance. Well, our second nicest performance, order 1. Order 1 algorithms take a fixed amount of time, no matter how big the data is. Constant time. That's kind of magic. Right? That's what your boss expects out of you at work. They'll give you twice as much work, you get it done in the same amount of time. That's a really sweet spot. And we will study algorithms that actually have theoretical order 1 performance. The classic example there is a hashing algorithm. So that's a way to store and retrieve information in a fixed amount of time, no matter how much information there is, which is really nice. The sort of ultimate theoretical limit is order 0. That's an algorithm that takes no time. So if you come up with that, that's really good. All right. So what I want to do is, we'll come back to these and talk about them in more detail when we talk about sorting and searching. But with this general overview of order of complexity, I want to start thinking about operations on arrays. That's a horrible spelling of operations. So let's think, O of -1 would be even better. Then you got time travel, because you actually gain time the longer your problem. Maybe that's the key to time travel. Maybe we just need to find an order -1 operation, and then just keep doing it until we get back to whatever time we want. That would be a fantastic SLP. If you can figure out even a theoretical order -1 algorithm, then we can just code it up in C and travel back in time. Good SLP. Do it. Yeah, you can do it as a group. That would be cool. In fact, I'd let a larger group work on that. I'd let you have 4 people. All right, so arrays of data. So yeah, we'll tag that one as time travel. See if anybody follows these indexes. So let's think about just plain old integers, okay? And just a plain old array, so integer, data, bracket, whatever. And let's think about different things we do to arrays of data. So you may want to insert new information into an array. You may want to search for something in your array. And let's list some possibilities. So suppose you just have an array of data. It's just an integer array. It's got some number of things stored in it. And I want to add a new piece of information to this collection. So I've got, integer data 1,000. I've got something that tells me how many things are in that array. I'll just call it num, right? And I want to add something to that array. So one possibility is I'm just going to, just tack something onto the end of the array. First number that I have, I'll just put it at data bracket 0, and I'll increment my num to 1. The next piece of data that comes along, I'll put it at data bracket 1, and I'll increment num to 2, and I'll just use num to show me where I can store my next piece of information. Alright, so inserting is an order 1 operation. If I have nothing in my array, it takes me, a few steps to add something to it. Basically, I store my new piece of information at data bracket num, and I increment num. If I happen to have 600 things in my array, it takes me the exact amount of work to add something new. I just store my information at data bracket num, and I increment num. So this is an order 1 operation, right? No matter how much stuff I have in my array, it takes me the same amount of time. Now I'm not worried about the case where my data overflows and I have more than 1,000. Let's assume I have enough space here. Inserting is order 1. How hard is it to search my array for something? So what kind of procedure would I use to search for a piece of information in my array? So you could look at every single element, and there's really not a whole lot else I could do. Assuming that my array is unsorted, because I've just been inserting at the end, the only way I can search for something is check every single piece of information and iterate through it. So if my array is completely full, this could take 1,000 operations. But if I have n pieces of information, worst case, it's going to take me n operations to search through the array and find, hey, it's not in there. Best case, I start with element 0, and there's the thing I'm looking for. Took a single operation. So it could be anywhere from, 1 operation to n operations. On the average, it's going to be n over 2. So this would be order n over 2. Well, here's the thing about these orders. We can simplify the heck out of this expression inside. Suppose we have something which is order n over 2. Well, if n is 10, n over 2 is 5. If n is 20, n over 2 is 10. If n is 100, n over 2 is 50. What we're seeing here is still linear, though. If we double n, we double how many operations we need. If we increase n by 10, we increase the number of operations by 10. So order n over 2 is exactly the same thing as order n. So yeah, we could talk about worst case scenario, but I'm just going to talk about averages. We won't worry too much about those details today. But either way, whether we come up with n or n over 2, we can still write this as order n. All right, and order n is kind of unfortunate. It's going to take a long time. So how can we improve our search performance? We could sort it. So let's have a sorted array. And if we have a sorted array, how quickly can we search it? I mean, we can at least do order n because we could still just search every element, but can we do something better if we have a sorted array? If we knew the index constant time, well, we'd have to search for the index. So let's just suppose we have a sorted list of data of integers. And I want to know, is the number 17 in there? Well, I could, check. So I could do order n. I could do, on average order n over 2, because usually by the time I get halfway through, I'll either have found it or I'll find a number that's bigger than what I'm looking for. Here we go. Okay, so we could cut the data in half. We could take something in the middle and say, hey, is that the number I'm looking for? No. So let's say I'm searching for 17. So I start in the middle and I say, is this the number I'm looking for? No. Is this bigger or smaller than what I'm looking for? Well, in this case, it's bigger, so I don't have to look at any of this data. Because if 23 is too big, all the numbers after it are also too big. So I just threw away half my numbers. One operation. So now I do the same thing. I start in the middle, and I look at the 5, and I say, is that the number I'm looking for? No. Is it smaller than what I'm looking for? Yes. I don't have to look at any of these numbers. And I've thrown away half of the remaining numbers I had. And each time I do this, I'll cut my search problem in half. This is the high-low game we did in 224. You're absolutely right. Right? That's why high-low works. Because if you didn't know the high-low algorithm and someone thought of a number from 1 to 100, it might take you 100 guesses. But if you do this cutting in half business, right, pick a point in the middle, see if their number's higher or lower, you're effectively doing this nice search algorithm. And so this is going to take us the number of times that we have to cut your list in half before we get down to one piece of data. And that's basically log n. And usually when we do logarithms in here, we're thinking log base 2. But it's a linear factor from log 2 to log anything else. Yeah, this is how CS builds on itself, absolutely. So searching, really efficient. Remember, we like log n, right? If n increases by 1 trillion, log n is, 40. It's a small factor. All right, the question now is, how do we insert into a sorted array of numbers? So I've got my array 2, 3, 5, 7, 11, and I want to insert the number 9. What do I have to do? Right, I used to just put it on the bottom. But since our array is supposed to be sorted now, I can't just, add a 9 down here. Okay, so do the high-low until you find the spot you need. And then what? So I discover that the 9 should go right here. Then shift everything down, right? We got to make space for it. And now the 11 has been saved down here, so I can put my 9 in here. All right, memory of a computer is a linear thing. One after another after another. So if I want to make space, I got to take the last thing, move it down, take the thing before that, move it down, take the thing before that, and so on. And depending on how many things come after where I'm inserting, I have to do that many operations, that many shifts. Best case, I'm trying to insert the number 10 million, which comes right here. I don't have to move anything. Worst case, I'm trying to insert the number 1, which comes right here. Everything has to get moved down. That's n operations. So average case, this is order n. Yeah, that would be a pain if that's how our human memories worked. All right, so arrays of data, we can choose to be very efficient in inserting and really inefficient in searching. We can do a more efficient search job, but then get terrible performance when we insert. And, you know, sometimes these are okay. If we have a fixed set of data and we're going to build it up and then we're not going to mess with the data itself, we're just going to search it for the rest of eternity, doing a sorted array is not a bad approach. You pay a penalty when you build the array, but then, you know, it's pretty quick to search it. But we would like to do something that sort of gets both of these. Right? We would like to, in particular, be able to keep our data sorted, but improve our insertion time. Now, the reason our insertion time is so bad is because of this way that memory is organized. Because when we make an array, each element of the array is stored at the next location in memory. If it's an array of integers, if this element is stored at location n, the next element is guaranteed to be at location n plus 4. And there's no way around that. That's important because that's how the compiler writes code to access an element from the array. It takes the index, multiplies by the size of the element, adds to the base address. But if we had the option of storing the next element of this array somewhere other than the next location in memory, we could break this order n issue. So here's our idea. Store element n somewhere other than n times the size of the element plus, you know, address of the start of the array. So there's a formula you can come up with. Take the address of the start of the array, multiply your index by the size of the elements, add that to the base address. That's the address of the nth element. If we had a way to store this thing somewhere else, then we wouldn't have to shift everything down. So here's what we have. We have our data 2, 3, 5, 7, 11, 23. And let's say, you know, this is stored at location 400. This is stored at 404. This is stored at 408, 40C, 410, 414. So these are hex addresses. And we want to put a 9 in here. Well, with an array, there's no choice. The 9 has to go at location 410, which means the 11 has to go at 414, and so on and so forth. So here's what we're going to do. We're going to break this dependency between indexes and locations. We're going to come up with a different way to store elements in this array that aren't automatically consecutive in memory. And once we have that ability, then we can just go ahead and we can just squeeze this 9 into here, and it becomes an order 1 operation. Well, how do we do this? Right now, we know where the nth element is stored. It's n times the size of the element plus the base address. If we're not going to use that formula, what are we going to do? We're going to have our data 2, 3, 5, 7, 11, 23. What if, in addition to storing our actual piece of data 2, we also stored the location in memory where the next piece of data was? So actually, let me go back to this picture. So what if we stored a 2, and we also said, hey, our next piece of data is at location 404 in memory. And then at location 404 in memory, we stored a 3, and we said, hey, our next piece of data is at location 408. And at location 408, we stored a 5, and we said the next piece of data is at 40C. And at 40C, we stored a 7. Right now, it says the next piece of data is at 410. And at 410, we store the number 11, and we say the next piece of data is at 414, and so on. Well, now if we want to insert a 9, what do? Find somewhere in memory to store the 9. It doesn't have to go in between the 7 and the 11, but maybe down here at location 480, we're going to store our 9. And so when we store this 9, we're going to take the number that comes before it, which is the 7, and we're going to say, hey, 7 is not followed by the number at location 410. 7 is followed by the number at location 480, which is our 9. And this number 9, we're going to say that's followed by, well, what should it be followed by? It should be followed by the 11, which is the number at location 410. And so in this set of information, we have our original array with a 9 squeezed in between 7 and 11. And the way we use this is we start with the first element, which is a 2. This tells us where the second element is, which is a 3. This tells us where the third element is, which is a 5. That tells us where the fourth element is, which is a 7. But the 7 tells us the fifth element is down here at location 480, which is a 9. So the 7 is followed by a 9 now. And the 9 tells us the next element is at location 410, which is an 11. And so we've got a 2 pointing to a 3, pointing to a 5, pointing to a 7, pointing to a 9, pointing to an 11, pointing to a 23. So this is a linked list. Linked list, not lists. So this is a chain of data where each piece of data points to the next piece of data. And so we're going to explore this and figure out how to code this and look at some of the details around this for the next few weeks, basically. And somebody asked in chat, wouldn't this be harder to search? Well, we can't do a bubble sort on this anymore, right? Because the trick to searching for log n was, I said, check the number in the middle first. Well, if it's an array and we know we have 50 pieces of data, we just start with element 25. If you have 120 pieces of data, we start with element 60. With a linked list, there's no way to jump into the middle of the array, the list, right? We always have to start at the beginning and follow these. So our linked list is going to insert with, once we know where to insert, it's going to be an order 1 operation. But to get to the point where we need to do the insert is going to be order n. And to search is going to be order n. So at first glance, this is going to look worse than a plain old unsorted array. It's going to take us, roughly n operations to move to the place where we want to insert, and then the insert's very quick. That's because the search is order n. But once we're done with lists, we're going to go on to binary trees. And binary trees are going to restore the ability to play high-low on a linked list. And once we do that, inserting is going to be order log n, and searching is going to be order log n. And that's going to be our sweet spot. Doubly linked list will have pointers going backwards as well as forward, because this list that I've described, we can only start at the beginning and move forward. We could also have pointers that go backwards, so that once you get to a piece of data, you can back up. And we'll play around with all of these variations and nuances over the next couple of weeks. So this will be PA1, this will be PA2. Okay, your first two programming assignments will deal with linked lists. So we'll start digging into some of the code for this tomorrow, and that will let us talk about the first large programming assignment. So we'll start from there tomorrow morning. All right, have a good one. I'll see you next time.